We're going to cover the solution to a homework problem on how to do symbolic manipulation within Python. Come to the course website at APMonitor.com, CHE263, and then go down to the homework and you'll see the notes here, the homework notes. Go down to assignment 17. You can see a PDF version of it here, or if you just want to download the files, you can get the IPython notebook. Okay, so I'm going to open that up. I downloaded it. It came to my downloads folder. I'm going to go ahead and extract it. Right click, extract all, and extract it here to the desktop. You'll see two files there. One is homework 17 IPython notebook. The other one is homework 17 version 3 IPython notebook. So if you have an older version IPython notebook, the other file will work for you. Okay, so I'm going to start up the IPython notebook. And so the SymPy is what we're going to use for the symbolic manipulation. In this, we'll go through a couple different examples with derivatives, integrals, just setting up variables, some very simple things to just a little bit more advanced. So if you open this up, this is the homework 17 on symbolic math. And the very first thing that we're going to do is go ahead and import the package. And there's a couple different ways to do this. I prefer to do it this way. You import it as SP, so you don't have name conflicts with some of the functions that you're going to be loading. I have S as SP. Another popular way, you can import this as from SymPy import all, and then you don't have to start the some of the expressions with SP dot. Okay, so with the way I've done it, we'll do sp dot init printing. Okay, and that's going to do some of the very nice output that we'll see later. And then make sure you just run that, and we'll go on to the next one. Okay, so we want to set up some variables x, y, and z. So there's a couple different ways to do this. You can do x equals symbol. Okay, x. Or another way that you could do it is just do your list of variables here and do symbols. Okay, symbols, lowercase there, and we'll just do y and z. Okay, so we've got a couple symbols. We can also get just a generic function. Okay, and that's going to be the function. I'll call that f. Or we can just create a new function like g equals, let's do x squared plus y squared plus z squared. Okay, and then if I just print g, for example, I can see the expression for g. Okay, so it converted it to LaTeX for me and it exported it. Looks really good. There's a couple other ways to be able to print that function. Okay, you can do print g. You can also do sp. So we're going to use a SymPy and then the double P print, and then it kind of formats it a little bit better. It's kind of in between the LaTeX way, which is the best, and just the print function, which is kind of the most text-based. So this one looks a little bit more like the expression that we're going for. Okay, so we've got our variables x, y, and g, and then functions f, f and g. Okay, so we want to set an expression for the following. Okay, so we'll have, let's just do h is equal to, we'll do x squared plus 2 times x minus 5. Okay, and then if I just put h there, I'll see that it output that function. Okay, then we want to evaluate this function at a value of 1.5. Okay, so to do this, what we'll do is use the subs function. We'll substitute for x, we'll substitute 1.5. And then if we just print that, okay, then we'll be able to see what the value is. That's 0.25. Let's do it again. But now we'll substitute, instead, we're going to substitute z for x. Okay, so we'll do that symbolically. Just put z in there. Okay, so now we have it in terms of z. And then let's do another one, which is going to be, we'll substitute y squared for the x. Okay, so there I have it in symbolic form. Okay, so let's go on to problem 2 now. Now that we have the basics on how to set up variables, functions, substitute in values for those functions, we want to now go ahead and simplify the following expression. So I'm going to create a new function, which is just f x squared minus x minus 6, put some parentheses around that, and then divide it by x squared minus 3 times x. Okay, so I've got my expression there. Okay, that looks great. But now we want to simplify it. Okay, so I'm going to use the sp dot simplify, and I'll simplify f. Okay, and it comes up with, it was able to cancel some things out and simplify the expression. Okay, so now we want to expand this one. I'll just, again, do x plus 1 to the third power, x minus 2 squared. Okay, and then we'll do sp dot expand. Okay, and then we have, it's multiplied it out. It just gives us a polynomial. Now let's say we want to factor this expression instead. So let's come up with our expression to the 4th minus 36 times x cubed plus 99 times x squared minus 6x, okay, minus 144, and then we'll do sp dot factor, and we'll factor f. Okay, so we factored that polynomial into the individual elements there. Okay, so problem 3. So this was simplify, expand, and factor. There's a number of other expressions that you can use to work with these symbolic equations as well. Now we're going to go on to derivatives and integrals. So let's go ahead and just define our new function. This one's going to be sine of x squared times, and then we can't use sine here. We actually have to use the SymPy sign. Okay, remember how we did the NumPy before? This time we're going to use the SymPy sign, and then we're going to square that. Okay, and then we're going to multiply by the SymPy exponential function as well. Okay, so let's go ahead and see what this one looks like. Okay, so that one looks good. And then we want to compute the symbolic derivative. Okay, so I can do SymPy dot and then the differential. Okay, and I'm going to do the y with respect to x, and there's my my differential. Okay, I'm going to call that z now. So this was a variable, now it's a function. This was a variable, now it's a function. And then let's go ahead and evaluate. We can evaluate it at that particular value as well. Okay, so we can use the z subs function and substitute in 3.3, and there we go. We've got our answer there. Okay, so if I gave a different, let's see, subs, somehow this is not, oh, I need to do SP. Okay, there we go. Let's see, I'm doing something wrong with the subs here. Let me see if I can figure that out. Oh, this was, oh yes, okay, this is going to be X. I needed to do Z subs, and then this is going to be, I'm going to replace X with 3.2 instead. Okay, so I have my function, which is Z, and in that function I'm going to take all of the X values and replace those with 3.2, and then I'll evaluate it, and there I have 74.2. Okay, so let's go on to the integral now. We want to evaluate this integral symbolically. Let me go ahead and create a new function. I'll call this y, or I can call it f, is x squared times, I'll do the SymPy sine, and of x squared. Okay, so there's my function that I'm going to integrate, and then I'll say that my new function, my integral of this is that's going to be the integrate. Okay, and I'll integrate f, and then I'll do a tuple here, so 3 symbols or numbers. I'm going to do it with respect to x, and my lower limit is going to be 0, and my upper limit is going to be 5. Okay, so it's going to evaluate that, and then if I just print out g, then it will evaluate this and then return the integral. Okay, so there it is. It looks a little bit messy. If I do something like print g, it's going to look even a little bit worse. Okay, so it's not too bad. And if I do the SymPy print, and it's going to look really bad. Okay, so that doesn't make a lot of sense. But let's say we wanted to just evaluate this. I can also do g.evaluate function to come up with kind of a numerical answer for this instead. Okay, of it being symbolic. Okay, so it's negative 2.2. All right, let's go on to problem. So this asks for symbolically right there. So let's leave it as a symbolic. We'll do it as a symbolic form instead. Okay, so it's going to take a little bit, but there you go. You have the symbolic form of that integral. Okay, so now we want to go on to problem 4. We want to solve the roots of the following equation. So we're going to use the EQ function and the solve functions to be able to solve this. Okay, and then we'll evaluate it at a particular value. Okay, so we want to use the first of all the equation one. Okay, so I'm going to come up with y is going to be SymPy and then equation. And the way you use this is you put the left-hand side of the equation on the left right here, and then the right-hand side is going to go right here. Okay, so let's start off with the left-hand side. That's going to be to the x to the third plus 15 times x squared. Okay, so that's going to be on the left-hand side. Now on the right-hand side, that's going to be 3 times x minus 10. I'll go ahead and print out y just so you can see that. Okay, so there's an equation that we just created. You got to have the left and the right sides to that. Okay, and now we want to solve it for x. So let's go ahead and just do z equals SymPy solve, and then we'll do solve this equation y, and we'll solve for x. Okay, so we'll get x on one side, and that's going to equal something on the right, and then we'll print out z. Okay, so here it is. We've got 3 different roots, and they're all separated by commas. So I could do z0. Let's see, I'll just do z0. That would just give me just that first root. Okay, it gave me 3 before separated by commas. I'll just take the first one. But let's say we want to evaluate this at different. Let's evaluate it now. Okay, so I'm going to insert something below here just to be able to separate these two. So we could do something like, let's just print z0, so that's going to be the very first element, and we'll evaluate the function. Okay, so that's going to come up with a number. Okay, so there it is. It's imaginary, has an imaginary portion to it. Okay, if I get the other 3 in there as well, or the other 2 in there as well, I can do z1 and z2 and then be able to show those. Okay, so let's say I have a kind of a long list, a lot of roots there, and then I could do something like a for loop. So let's just do for w in z, and then we're going to say print w dot evaluate function, and then that will print those same 3. Okay, so just a little bit more efficient. I just cycled through with a for loop for every element in z, and then each element is then w, and then I evaluated that and printed it out. Okay, so there are my 3 roots that I have. Okay, so let's go on to part B. Now here are three equations, x, y, and z, and I want to be able to solve these. And then also compare that with the SymPy optimize. So I'm going to first of all go ahead and just set these up as, let's just, because I've written a couple functions that are y and z, let's go ahead and just set these up as symbols again. Okay, x, y, and z. Okay, so now they're symbols instead of functions. And then I'm going to come up with an equation 1. And let's do this equation function. And then I'm going to have x plus y plus z on the left-hand side, and then 0 on the right-hand side. Let me get two more equations here. Okay, and this one is going to be 2 times x minus y minus z. Then on the right-hand side, that's going to be 10. And let's get y plus 2 times z, and then 5. Okay, so now to be able to solve this, I'm going to use the solve command. Okay, the SymPy solve command, and then I'm going to have equation 1, equation 2, and equation 3 just separated by commas. And then I want to be able to solve for x, y, and z. Okay, so I put what I want to solve for right here, and then the three equations on the left-hand side. And then that should give me a solution. Okay, so it tells me what x is, what y is, and what z is as well. Okay, so that's how I use the solve. But let's go ahead and do this with SymPy as well. So I'm going to go ahead and insert a cell below. And that was from SymPy optimize import fsolve. Okay, so that's a function solver. And then we're going to do, we'll define a new function, and I'll say that's a function of w. And the very first element of w is going to be x. The next one is I'll just say that's going to be y and z. Okay, y and z, and just change the element numbers there. So just, I don't have to do this, but it just makes it a little bit easier to see the functions. I'll say f1 is going to be x plus y plus z. f2 is going to be 2 times x minus y minus z. And f3 will be y plus 2 times z minus 5. Oh, I forgot the minus 10 there as well. Okay, and then I'll return these three, f1, f2, and f3. Okay, so there's my function that I can evaluate, and then I can just use, just get a result, which is fsolve, and I'll say that I'm going to use function f. Give it some initial guesses here, just zeros. And then if I solve that, okay, then I can print the result, for example. Okay, so that gave me the same answer. In this one, it didn't solve it analytically, it solved it numerically, so the values are going to be in decimal places versus fractions. But it gave me the same answer that I had above, that you can see in output 37. Okay, so let's go on to part C. So let's solve the following differential equation symbolically using the dsolve, or the differential ODE solver that we have. Okay, so let's create a new function f. That's going to be sp.function of f, and then we're going to say that y is going to be sp. Now there's this one, I'll type it and then I'll explain it. Okay, so I'm going to use the derivative function, and I'm going to say that I have f of x, derivative with respect to x, so that's on the left-hand side, and let's see, and then I'm going to subtract, so I'm going to put everything on the left-hand side. So then I have x times, and then sp cosine of x. Okay, so there's my differential equation, and then I'm going to solve for f of x. Okay, and then let's okay, so let's just go ahead and print that out and see what it comes up with. Okay, so there is, I've solved this differential equation, solved for f of x. Okay, and then let's also do this just another way. You know, if I wanted to just integrate the right-hand side, that would give me the answer as well. So let's just go ahead and do z equals sp dot integrate, and then we'll integrate x times sp cosine of x, and then let's just go ahead and print out z. Okay, so it gave me the same answer, and I'll print y as well. Okay, so it gave me the same answer, but the one, it just showed me f of x equals a constant plus that same answer that I got by integrating x times set point of, SymPy of cosine, okay, x. Alright, let's go on to the next one, which is problem 5. Here's a little bit about matrices with SymPy. Okay, so we want to, we can do from SymPy, import matrix. Okay, if you just want to import that, let's just try it with a equals sp dot matrix. Okay, and I'm going to have 1, 2, 5. That's going to be my first row, separate by a comma, and then I have 3, 4, and 6, separate by another comma, and then these are all square brackets inside here. -1, 0, and 3. Okay, so let's see if that worked. I'll print A. Okay, so that's just a matrix. If I do something like sp.pprint, it looks a little bit more like a matrix. And if I just do A, I think this version just has a lot of weird, doesn't like it, but it came out with output 47. It shows it in LaTeX there. So I don't like all these error messages, so I'm going to use the sp print. Okay, and there is my matrix. Okay, so let's do B as well. Do matrix, and in this case B is just going to be 1, 0, -2, and let's print that out as well. Okay, so we have A and B that are printed out there. Okay, B is just a vector, a column vector. Okay, let's go on to part B. Now we're going to solve this system. Okay, this A equals A times x equals B. We want to solve for x, so we have to take the inverse of A, multiply it by the left-hand side of both sides, and we'll get inverse A times B. So we want to solve that. So I'll just show you one way to do it. Do sp pprint, and then A inverse. Okay, so we'll print that. That's the A inverse, but we're going to multiply that by B, and that gives us our solution to x. Okay, another way to do that is there's an let's see, what is it? ALU solve. That's a lower upper form. It does might be just a little bit more efficient for big matrices, but that would be the same answer that you'd get for the first one. Okay, so those are two different ways to solve this system. And then for the matrix A above, return the middle row and the middle column. Okay, so to do that, we can slice this just like we've done in the past. We can, so let's just do, I'll do psp.pprint, and we'll do A, just to be able to look at our A matrix, okay? And then we just want to take the middle row. So let's print out A. I'll do 1 to 2, 1 to 2. So it's just going to take, you have the 0, and then 1, and then 2 elements. So we're just going to do 1 to, oh, I didn't want to do 1 to 2. I want to take all of those columns right there. Okay, so I just took the 3, 4, and the 6 from those. Now let's just go ahead and get the column, the middle column. So I'm going to copy that, and let's put the all of the rows with just 1 to 2 on the column. So it doesn't include the last one, it'll just be the middle one. And so then I have 2, 4, and 0. Okay, so I've got those. I've sliced those. Just took slices of them. If I did something like 1 to 3, for example, I just get you know, those the last two, or I could just say 1 to end. Okay, and I'd also get the to the end. Okay, if I did 0 to -1, for example, it'd take just the first and second. It wouldn't take the last one. So I go back one from the last, and I just take a slice of all of the columns except the last one. Okay, so that's a little bit about slicing these matrices. Let's go ahead and create just a zeros matrix, and then fill in just a couple. I'm just going to create a new matrix M, and we'll do the zeros, 2 by 2. Okay, and then let's just go ahead and show again all this error here. It comes down and it's going to show you the zeros. Okay, but I don't want all those errors, so I'm going to use SPy print, and let's just look at that. Okay, so I've got that, and then let's see. Let's go ahead and change some of the values of this and just look at what it gives us. Let's change the 1, 1. Okay, so that's going to be the bottom right-hand corner. We can change that to 3, for example. Let's change the first, so the second column, first row. We'll set that as 1.5. I think you can also put an X in here. Let's just go ahead and check that out. Okay, so you can also have variables in there as well. Okay, so there's X squared, for example. Okay, so it can be symbolic or just numbers as well. And then if we did something like M inverse, okay, then let's go ahead and see what that would give us. Okay, it didn't like that. Not invertible. Okay, so some of these you can invert, some of them you can't. Okay, again, that one didn't work either. Okay, so some of the symbolic stuff it doesn't like to invert it, but if you just had numbers in there, okay, and then we'll do M inverse. Okay. Whoa, okay, that didn't like that either. Oh, you know what? It's because it isn't invertible. That's why it's not working, okay? Because I have those 2 zeros up there. So let me just change one of those. Okay, and let's try that again. Oh, there it is. Okay, so it worked now. Let's change this back to X, because I'm just kind of curious to see if it's going to work. Ah, there it is. Okay, great, it works. Let's change it to X squared. Fantastic. Okay, so it works. You got to have something that can be inverted, and then it'll give you a symbolic solution to that answer. Okay, so this concludes assignment number 17. I'll go ahead and post this solution video right there next to the files.